So the schedule this afternoon is at principal at 3 p.m. There'll be coffee out there with probably like 95 people. And then at 3:30 there's two 30-minute talks, one by Eric Rupert and one by Andrea Richa. So that's the schedule for the rest of the day. And so we continue on our theme of processing in memory, and Hongbo is going to give our next talk.
Okay, so my talk will be about PIM-trees, about our prior work. And I think the idea of this talk is to give some intuition on the fundamental techniques that is used and reused in our PIM indexes in more detailed way. So hopefully you can understand that. So it can motivate some new ideas in this open area of processing memory. Probably you can find some other memory-bound workloads. And the way I'm doing this is I'm trying to show concrete technical examples. So this talk is going to be much more technical than the prior one. And I'll focus on the PIM-tree because many techniques are first developed there and it's reused after in later works. So PIM-tree, it's a skew-resistant index for processing memory. This is covered by Phil, so I go through it quickly. We want search tree because it's important and because it's victim to memory wall. And we want the search tree to support operations, especially those related to ordered operations. And we do batch parallel index. And our work focuses on skip lists, but we believe that it should generalize to other solutions like B-tree. So what is a batch parallel search tree? We have an example here. Suppose we have a traditional in-memory batch parallel search tree, and we want to do point queries. So we have an array of point queries, and they start from the root, which is node 0. And they all need to read node 0, and so CPU read node 0, and all these queries are processed in parallel. So some goes to node 1, and some goes to node 2 according to their keys, and those go to node 1, read node 1, which is CGM here, and node 2, read node TX, that's node 2. And they can go one step further. So these are read to CPU to actually push these queries forward in the tree. And then we are on the third layer, and then they fetch more nodes. And finally, we get the results. It can be like a value, that's one case. And so what's the actual communication on the memory bus we have in this case? So for a B tree of a block size B, it can be B log Bn in the worst case when there is no cache. When there is cache, this can be reduced. We can make this tighter. But if your tree is really big, cache cannot help you that much. That's the idea.
So do you assume like it comes sorted?
Yeah. So the idea is that you will not have a very large batch in this case. Otherwise, this will be in memory, and processing this can cause lots of data movement on the memory bus. So we think this should be small, and it's very likely to be in cache. So we can store that in cache, which, because it's small, it's not very expensive. So that's the idea.
But in a B tree, it has to be the size of the block, right? Of the bit.
You mean what? You mean this B? What? What should be the size of the block?
The size of the leaf should be the size of a block, right?
I think that's the same concept. You mean, yeah, so the size of the leaf is the size of the block.
B here is the size of the leaf?
It's a parameter for a B tree. That's the size of the leaf and also the size of internal nodes. I'm kind of not digging into the details of B tree and B plus tree, etc.
Maybe I missed, like, is it like, have you defined the batch size something? Or no, not yet.
This is traditional in-memory. It's not our solution.
Oh, yes.
It's kind of a baseline. So what we do, for PIM, there are basically two things we can do. We can kind of shuffle the data here, probably do some replication, and we can schedule the operations between PIM modules and CPU. And we want load balance. We want low communication on the network, the memory bus. And we want low space, no overhead, and low CPU work and span as well. So the final target. So this is covered in the prior talk, so I'll go through it very quickly. That's the idea is that if you do range partitioning, you can have loading balance, and this is not something you can solve easily. And this is also covered. I have an animation here. Suppose you have a query that's 15, and you randomly shuffle stuff. So first we'll go to PIM-2, that's some communication. You can probably send it back to CPU, or even if you leave it there, still it's going to go from 2 to 4, and 4 to 1, and 1 to 2, and all the way. So there's a log n communication. And that's a problem. We have this kind of contradiction here, and we show that we can actually solve it. So what's the insight? The insight is that trees are quite special. So the upper part of the tree is frequently accessed, but the size of the upper part is exponentially small. And updates to them are exponentially infrequent when you are doing search trees. So we can choose to replicate the upper part. But the replication strategy is more complicated, but the basic idea is to do replication. Okay, so this is also covered before. We have a 2-layer structure. That's a first idea in replication. Is the upper part is small, so we replicate the upper part. And we select the lower part to have a size log p, so the upper part is small enough, so we can do replication. And then we can do query for that. The upper part is cheap because it's local and it's just one round trip and constant size for a query. So communication is reduced to log p here. It's already independent from n in this case. It's the height of the lower part. And still, we have the problem of loading balance. This is also covered before. We can have a loading balance even if we have a randomly distributed lower part. And our solution is a push-pull search. Yes. Oh, it's going to. So one thing I want to emphasize here is the push-pull search is somehow a win-win in our case, because we want to achieve 2 things. One is that we want to achieve load balance. Another thing we want to achieve is we want to achieve low communication. And the pull side in this case actually improving both sides. First, compared with sending many queries, we are just fetching a constant size stuff, so we are actually reducing communication. Meanwhile, while these queries should be processed by this green one, if you do push, that will cause loading balance. But now you are pulling the data instead, so this green one is no longer in this busy state. So we also achieve load balance. So that's a win-win. We are reducing communication and we are achieving load balance. So what's next after we pull the data there? We just run the data, we just run the query there, and we get the next frontier of the tree search. And the push, we'll need to get the data back. So we get the next frontier. That's what we have in the first example. And we can go step by step until reaching the result. That's a standard technique of push-pull search. I think it's quite fundamental because that's what you do in this is what you do in a distributed setting. You send your task to the data. And this is what you do in the standard shared memory setting. That's you fetch the data to the CPU. So it's a combination of 2 very standard techniques. Okay, something slightly more for push-pull search. That's push-pull search doesn't magically solve all problems. And we have an example here that's, suppose you are doing the range partitioning scheme and you have loading balance. Can push-pull search solve this? So now you have to decide whether you push your queries and cause loading balance, or if you want to pull, you need to pull the whole subtree, which is very large in space. You may not hold it, and it's lots of communication. So it's not the silver bullet that solves all the problems. But you can probably do it if the object itself is small. That's kind of the insight I'm trying to tell here. Yes? That's for push-pull search. Any question?
So my correct that all these push-pulls are explicitly, like the programmer actually has to say push and pull this specific data?
Yes, the programmer will need to say that I want this data back to CPU, or I want to send these queries to the PIM.
So is there an implicit assumption then in these PIM architectures that this is a single application in the sense that the cache management is essentially explicit? How would you do it if you had another application that...
I see. That's a different problem.
Okay.
That's not what we are considering now. But currently, the current hardware is just we have full control of the PIM module. But like virtualization stuff is an interesting topic. Okay, I'll move on to shadow subtree. This wasn't discussed before. So shadow subtree is also a very simple solution. It's just we do eager pre-caching. So why we need this? Because we want to rebuild some vertical locality in the lower parts. We want to further reduce communication. But we cannot achieve full replication. We can just do a partial replication because of the space constraint and update cost. Too many nodes in the middle. So we slice the middle layer, we call layer 2, and every node cache their descendant subtree. What's a descendant subtree? So 5 is not a descendant subtree for this because 5 is accessed this way. So that red box is a descendant subtree for that negative infinity in yellow. And we just cache everything in the descendant subtree at the same PIM module with this node. And we keep all the pointers. And this is done on the whole layer 2. Why is it helpful? It's because with this shadow subtrees or pre-cached subtrees, we can go through layer 2 just by one round trip. So it's all local. This improves locality. So we have our final structure. It's very close to our final structure. We have 3 layers, a fully replicated, an eager pre-caching, and randomly distributed. And I have an example for that. We have a batch of queries, and we start by the replicated top layer. We send the queries, and it's executed there, and we get our frontier. That's 2 nodes, node A and node B, and many nodes B here, so probably that's too much. So we'll do a pull. So we'll pull that node B. We'll pull only this node, but not this full cached stuff. So this is constant size. And this enables us to go forward by 1 step. And so we get 2A, 2C, and 4D here. Because 5 and 6 actually goes to this direction, and 7 to 9 actually goes to this direction. So it's decided by the keys. And now we think 4 is good, so we can do push. And they are all pushed to these nodes, and these shadow copies are utilized. So we get to layer 1. And in layer 1, we can only do traditional push-pull. There's nothing else we can do because we do not have replicas there. OK, so here's the most technical part. I'm trying to show you why this is good. So the basic idea is that we carefully select the heights. Layer 3 is log p away from leaves. It has full replication, and its search cost is constant because of full locality. It's n over p. There's n over p nodes because it's high in the tree, and p replicas because of full replication, and so linear space and constant update cost per operation in a random way because it's rarely updated. So the hardest part is the middle part. The search cost is still constant. This is obvious for push. It's less obvious for pull. But you can achieve this by carefully select the parameter, the threshold, when you want to pull. The idea is that when you get more than log p queries to the same node, you do pull. So it's probably you spend constant communication to push some queries 1 step further. And you have multiple steps, so they cancel out. So you'll still have constant communication. And there's n over log p nodes because it's, again, high in the tree. And the number of replicas is log p because the way to analyze this is to realize that every node is replicated in all its ancestors. And this path has size log p. And update frequency is again because it's in the middle. So update cost is also constant after the search, the real updates, the writes. And layer 1, there's nothing more you can do for search. So it's log p because of its height. And there's no replica, so it's constant space and constant update. So what we get at the end is we have a log p search, and the actual update is constant. But for an update, you'll need to do a search, so update is also log. So that's what we get at the end. And the space is linear. And OK, so this is a final technique we use for PIM-tree. That's we are using a bit skip list rather than a real skip list. A bit skip list is just a chunk skip list. The idea is that we merge the horizontal nodes together into chunks. So, and we put these chunks in the same PIM module. So like here, 3 and 4 used to be separate and at different position, but now they're together. So it's just one chunk. And we want this because this helps us to avoid the horizontal intermodule communication. So this helps us reducing these communications because you should just go up to down. You should not take this now. And we have a chunk size. We have a parameter b for the chunk size. That's expected chunk size, and we choose b equal to 16. Yes. And we get, that's the end for our structure. Any question for the structure? OK, I'll move on. So what we get at the end after all these structures is that we get a load balance, and it's guaranteed against adversary workload as long as the adversary does not know our random choice in the skip list. And we reduce the communication regardless of this skew. So it's log B P per operation again for search and update, including inserts, deletes. And it's usually 3 or 4 communication rounds in practice, which is because P is a hardware parameter. That's the number of memory modules we have in the system. And we remain linear space. And recall that this is an experimental platform we have, and P is 2000 here. So log B P is just 1. It's actually smaller than 1. Yes, and it's 2000 PIM modules and running at 450 megahertz and has 64 megabytes of local memory. Yes, and this is covered. It's clear that we should be faster in the skewed case because partition solutions is really bad in this case. And I'll try to introduce more on how we are performing compared with traditional solutions. So compared with speed trees, we are like as good in queries. We are much faster over insert. So I guess one contribution to this result is that skip lists are fundamentally better at updates compared with speed trees. So B trees are better for queries. And this is about the communication comparison between PIM-tree and traditional solutions. So I want to introduce what these two parts are for. So the lower part, which is tiny, is the real communication between CPU and PIM in current hardware. It's measured. And the larger part here comes from the limitation of current hardware that the CPU cache is too small. So this is actually the CPU cache overflow communication. That's between the CPU cache and these traditional DRAM. So even though our algorithm ensures that the CPU cache cost is P polylog, it's actually P log squared P. This 22 megabyte is still not enough. So we get lots of overflow here. So that's the main contribution to our current communication. So the real communication between CPU and PIM is small. So if we have larger cache, this should reduce, and we have some experiments on that. And also, we are achieving better performance on some more real-world data sets. So these are the key takeaways. Prior words are vulnerable to skew, and we have some techniques that's quite fundamental, but they work well in our setting. And we have our code. So any question for this?
Did you consider range operations?
Yes, we actually consider range operations, and we particularly consider small ranges. So the idea is that, so when you have large ranges, so in case of communication, when you have large ranges, it's okay because you are sending lots of data anyway, and that's going to be kind of saved by save your internal stuff. And for shorter ranges, the idea is that I think the idea is that we are trying to broadcast this stuff. It's not broadcast, we are trying to fix the left side and the right side of the small range and try to track that throughout the frontier, the propagation process. So yeah, that's part of the paper, but I'm not talking about that here.
I should have asked Phil, I think, but okay, I'm going to ask. So, do you think that if this technology provides a primitive like an RDMA, like a remote direct access, would it be useful to have the CPU instruct the PIM to send data, but the CPU continues, right? Its execution. And then once the data are in the CPU, in the DRAM, in DRAM, somehow the CPU finds out and then goes and does whatever it has to do. Would that be helpful at all? And is it provided in?
Just to make sure I understand your question correctly, so what you're saying is that you're thinking if there's an RDMA technique that enables enable PIM module to write data to CPU cache?
Yeah, because sometimes you need to move data from PIM to
Yes.
the CPU, right? Not to the cache, the DRAM, I guess.
Yes, so first is that for this work, this is a bulk synchronous model, so I think it will not be very helpful in bulk synchronous model, but if it's a concurrent case, so one thing is that we know that CPU...
I was thinking in the other model.
Yeah, because CPU is actually doing that, right? Like CPU is working while reading, so yeah, that's kind of a different but interesting problem.
I see, okay.
Okay, I'll try to finish my second part. It's about PIM-tree. Here I want to illustrate how our prior techniques apply to these techniques. So I'll not go into many details. So radix-based indexes, we want them because we want to support arbitrarily long string keys, and like this example. And we have some different types of operations like longest common prefix, LCP, we have inserts, deletes, and we still have subtree query. And we still do batch parallel execution in this case. And this slide is the same. We still have this method. We still have these targets. And again, the main challenge of the radix-based solution is that the tree can be arbitrarily imbalanced in shape and height. The shape is dictated by the keys themselves, and the height is the length of the longest key, which can be ON in the worst case. So we do not have that observation that size is decreasing exponentially, so it's not true. So you cannot simply do a horizontal partition here and do replication on the upper and pre-caching for the middle. That's not going to work because you cannot just partition horizontally. So we have 3 techniques that I'll talk here, and many others. And the idea is that I want to say that actually this one is very much influenced by the push-pull search and chunking. And this one is very much influenced by our pre-caching strategy. But we will have to go through query try first. Query try is our technique to take advantage of a batch of queries. We have 4 queries here, and we build a try from that so that we can avoid the redundant work in the shared prefixes. This is done in CPU. Then we do a matching between the query try and data try. So this is a depth first search style. You match these 2 tries. And as mentioned, one problem is that something that's a node here may not be a node here. Something that's a node here may not be a node here. And your match can be somewhere between, in the middle, on the both sides. So that's the hardest part that we thought we were into.
So what are the rules, like why would you match those two, but there's some other edges in the middle that could match somewhere? What are the rules for matching?
Okay. So it's matching as these two are exactly the same. And I can try to introduce this by showing what this red part is. The red part is the longest common prefix for these queries, between these queries and the data try. So like here, we have a query that's 0, 0, 1. And the longest common prefix is actually 0, 0 because there's no 0, 0, 1 here.
No, I understand that. It's like why not 0, 0, 0, 0, for example, which is like, why not match, like on the left, right? 4 zeros is, on the left, the 4 zeros is somewhere in the middle of the leftmost bottom edge.
Yeah,
Why
you
do
mean here 0, 0, 0, 0 here?
Yeah, like
Because
why don't you match that?
There isn't such query. So suppose we have 5 queries, it's this one, this one, this one, this one, and 0, 0, 0, 0. Then we have a node here, that's for a query,
Oh, I
and
see.
we match that. Because we only have 4 queries. So this query try is from this set of queries, and that's what we want to solve.
Those are the only ones, okay.
Yeah, and that's the tool. So clearly this depth first search way of doing tree matching is slow because it can cause height IO rounds. And even if you try to do a simple parallelism, but even if you are top down bit by bit, it's still height. So we want some kind of parallel matching. And the idea we came up is we use hashing to achieve that. And the idea is that we have a data try here, and we try to decompose that into smaller parts. You can also understand this as smaller chunks. It's chunks of data. And for a batch of operations, queries, for example, we compress that into a query try, and we want to decompose that into the exact same way into sub operations to each block. So this is 1-to-1 match. If we get this, then we can run these blocks in parallel. That's ideal case. But how can we do that? We'll have example later. So the idea is to use the block root hashes. So for every these blocks, we have their root hashes, and we use these hash values to decompose this try to ensure that the decomposition is exactly the same. So here's the example. So we have a data try, that's the data, and we decompose it into 3 parts. The first cut is here, it gives the first, and the second cut is gives the first one. Second cut is here, I think. So this is the second one, and the lower part is the third one. And how do we do try matching? Is we have this kind of split positions at the root at 101 and 1010. And we want to split in the exact same way for our query try. So we split here at 101 and split here at 1010. So we get 3 blocks. And then we can solve this block separately in parallel. But there's a problem. This block can be very large. Suppose we get many queries all starting with 0. So everything will be in block 1. And this can cause loading balance if we just send this huge block to PIM module of node 1. This is where we have push-pull searches. As after you have this decomposition, you need to do push-pull search for each of these blocks to ensure you do not run into the loading balance problem by sending a huge block to a single one, to a single PIM module. Which, in other words, means that these blocks must be small. Otherwise, you are pulling a huge stuff. That's also bad. So if this is small, this is large. So that's the next problem. How can we manage the hash values? There can be many hash values. You cannot store them on a single PIM module. That's loading balance, that's problems. And distribution is not going to help as well because you really need to do matchings for these hash values. And our solution is a hierarchical structure. We try to make this a balanced stuff so we can do the pre-caching and replication. And the idea is also, I think it's kind of basic for trees. That's you do a hierarchical decomposition. And you cut it recursively into smaller parts. And at these cuts, you get a hash value. And you get a root hash value, so you have a tree. And that tree is polylog depth. That's what we want. So for our query trie, we can decompose in the same way in this tree, so we can finally get these small blocks. That's a basic idea. I'm not running into very details. But this is what we have at the end in the PIM. So I'll try to
The small blocks would be, in the number of these small blocks would be the same as the number of PIM modules or not?
No, not much more. So
you assign more than one to each PIM?
yes, because we want load balance, so we have small pieces that's randomly scattered.
And
Yeah.
what about locality? But it doesn't matter, okay?
Yeah, so yeah, that's again, the locality is a problem if you divide that too small, but it's kind of a trade-off here.
Okay.
You can still get very good results with, like, there's a sweet spot. We can achieve that. Yes, and I'll try to show you that why this is related to my first part of talk. So this is so imagine every such block is a block in every such node is a block in the radix tree. So this is after the blocking stuff, this is a tree. And we are doing decomposition on this. And the highest level decompositions are 1 and 3. This is replicated on all PIM modules. And after this highest level decomposition, we get two parts, the left side and the right side. So left side, this node is on PIM1. It has its own information and all information in its subtree. And this is the same. This is PIM module 3. These nodes have all information in its subtree. So that's the pre-caching that's happening here. So it's probably not very detailed here. So the idea is that for the highest, for this side, for the highest level in the decomposition, we do replication. And for the lower levels, we are doing a pre-caching. That's every node is caching all information in its subtree.
Do you support any updates?
Yes, we support updates.
Talk a little bit about.
No, I'm not going. I'm using up my time. Yeah, but the idea is that
Is it the same as what Phil said previously, like only inserts in batches but no deletes and queries? Or is it more
I
like
think
this?
these have inserts and deletes, but they are all in batches. It's not concurrent.
Okay.
Yeah, it's all in batches. And this structure by itself supports deletes because what I've mentioned in the first part of the talk, that this pre-caching actually supports deletes because the choose of parameters. This stuff is not going to be updated very frequently because we have those chunks. This is updated only when you like double the size of the chunk or shrink it by half. So it's kind of amortized or randomized so bit.
But do you have to rerun the decomposition, or the decomposition is what it is and you simply live with it somehow independently of the updates?
I think we need to update that. We are changing this, so it's not static.
Okay, okay.
Yeah, we need to change that. And the other techniques, like how can we reduce the hash computation? How can we detect hash conflicts? Because we rely a lot on these hash values. And how to do updates, that's not covered here. We have quite good results. We support arbitrary length in key strings. We still have linear space consumption. We have low I/O bounds, and that's independent of key length, especially in the rounds. And yeah, low I/O rounds and low communication amount. It's on the right side. Okay. So here are the key takeaways. We introduced PIM-tree. It's a skew-resistant radix-based index. And the three key techniques are, we have a query trie that's avoid the replicated communication. We have a trie matching that's a fundamental operator for the operations. And we have a hierarchical decomposition. Okay, so these are the key takeaways for the full talk. I'm introducing the PIM-tree and PIM-trie. They are both skew-resistant search trees. They are both skew-resistant data structures for PIM. One is a search tree, one is a radix tree. And the key techniques are the push-pull search, that's used in both of them, pre-caching, that's used in both of them, and chunking is used in both of them. But for PIM-trie, you need to do something more clever. And that's the end of my talk.
Time for one or two questions.
So I was wondering, like this, is this data structure can be made oblivious to the PIMs, like those modules, memory modules?
You mean the number of memory modules or what?
I mean, like when you implement that, do you use any of the memory parameters, like all those? You have like those.
Probably we can go back to the first. Yeah, we need the parameter p that's used to.
Yeah.
The p is used to decide the height of each
Height.
layer. Yes, so it's not oblivious
Not
of
oblivious.
p. Yes.
All right, let's thank the speaker again.